it is the subject that deals with conversion of heat energy to mechanical work and lays the foundation for understanding remaining subjects like IC engines, heat transfer, gas turbines, steam power engineering, refrigeration and air conditioning, thermal turbomachinery like compressors, fans, blowers, etc. The understanding of this subject needs the concept of the ideal gas. So let us define the ideal gas, which is also known as perfect gas. It is the gas which obeys all the gas laws like Boyle's law, Charles law 1, Charles law 2, Avogadro's law, etc. Let us define Boyle's law. The law states the pressure of a gas is inversely proportional to volume of the gas if temperature T of gas is constant for a fixed mass of gas. P is inversely proportional to volume if T is constant. Mathematically it can be written as PV is equal to constant, or P1 V1 is equal to P2 V2 if T is constant. Otherwise it can be said that if the pressure of the gas is halved, volume becomes doubled if the temperature of the gas is constant. In fact, the gas should be of fixed mass. Coming to the Charles law 1, which is also known as Gay-Lussac's law, for a fixed mass of gas, the volume of gas is directly proportional to absolute temperature of gas if pressure P is constant. Mathematically speaking, volume is directly proportional to T if P is equal to constant, or V by T is constant if P is equal to constant. V2 by V1 is equal to T2 by T1, provided T2 and T1 in Kelvin scale of temperature, or absolute scale of temperature, or thermodynamic scale of temperature. Coming to the Charles law 2, if volume of gas is constant, the pressure of gas varies directly proportional to absolute temperature of gas, that is for a fixed mass of gas. Mathematically, P is directly proportional to T if V is equal to constant, implies P2 by P1 is equal to T2 by T1, provided T2 and T1 in Kelvin temperatures or absolute temperatures. We have to add 273 to the Celsius scale to get the absolute temperature. The T1 and T2 should be only in Kelvin scale. If the pressure gets doubled, the absolute temperature also gets doubled if volume is constant for a fixed mass of gas. Now, combining Boyle's law and Charles laws, we get P is directly proportional to 1 by V. This is Boyle's law. And P is directly proportional to absolute temperature of the gas, which is Charles law. Mathematically, it can be written as P is directly proportional to T by V, or PV product is directly proportional to the absolute temperature of the gas, or PV by T is a constant for fixed mass of gas. That is P1 V1 by T1 is equal to P2 V2 by T2 if M is constant. This is known as thermodynamic state principle, which can be written between any two end states irrespective of thermodynamic process undergone between them. Replacing constant with product MR, we get ideal gas equation, also known as perfect gas equation, as PV is equal to MRT. This is very important equation because if we know any two properties of the thermodynamic system, we can get the third one by using this equation. In this equation, the R, small r, is known as characteristic gas constant. Why it is called characteristic gas constant? Because it is different for different gases. For example, R of air is 0.287 kilojoules per kg degree centigrade, or it can also be written as kilojoule per kg Kelvin. 1 degree centigrade rise in temperature is equal to 1 degree Kelvin rise in temperature. So it does not matter whether we write kilojoule per kg degree centigrade or kilojoule per kg Kelvin. M is mass of gas in kg. While using this equation, it is always better to maintain the pressure units in kilopascal. Then R will be substituted in kilojoules per kg degree centigrade. Volume in meter cube. Any gas which obeys this equation at all pressures and temperatures can be termed as ideal gas or perfect gas. Examples of ideal gas: hydrogen, oxygen, nitrogen, helium, neon, air, and even carbon dioxide can be taken as examples of ideal gases. Truly speaking, there is no perfectly available ideal gas, but all the monoatomic, diatomic, and polyatomic gases like carbon dioxide and even superheated steam can be taken as an examples of ideal gas. A real gas which does not obey PV is equal to MRT at all pressures and temperatures can be approximated as ideal gas at very low pressures or under high vacuums and at very high temperatures. That is, as P tends to 0 and T tends to infinity, a real gas almost behaves like ideal gas, also known as perfect gas. Ideal gas equation can also be written as PV is equal to nRT on molar basis, where N is equal to number of moles of gas. Capital R is universal gas constant, which is same for all the gases. The value of universal gas constant is 8.314 kilojoules per kg mole Kelvin, or 8.314 joules per mole Kelvin. N number of moles can be written as mass divided by molecular weight of gas. For example, 2 kg of hydrogen is equivalent to 1 kg mole of hydrogen. 29 kg of air is 1 kg mole of air, because molecular weight of air is 29. There is a relation between small r, that is characteristic gas constant, and capital R, that is universal gas constant. Small r of any gas, that is characteristic gas constant of any gas, can be calculated as universal gas constant divided by molecular weight of gas. For example, for air, which is an ideal gas, R of air is equal to universal gas constant divided by molecular weight of air, that is 8.314 divided by 29, which is equivalent to the 0.287 kilojoules per kg mole Kelvin. For hydrogen, R of hydrogen gas is equal to 8.314 divided by 2, because 2 is the molecular weight of hydrogen. 8.314 divided by 2 shall give the characteristic gas constant of hydrogen gas. In this context, because we are defining the perfect gas equation on molar basis, it is better to define Avogadro's law. The law states that equal volumes of all gases contain equal number of molecules under conditions of identical temperatures and identical pressures. That means, if we take two samples of gases at the same pressure and at the same temperature, and if their volumes are equal, it means that both the gas samples do contain the same number of molecules. Next, coming to the Avogadro's hypothesis, which is based on the Avogadro's law. 1 gram mole of any ideal gas contain Avogadro's number of molecules, yet normal pressure and normal temperature. which are also known as NTP conditions. NTP conditions are given as 273 Kelvin temperature and 101.3 kilopascal pressure. There is another hypothesis of Avogadro. 1 gram mole of any gas occupies a volume of 22.4 liters at NTP conditions. Coming to the specific heats of a gas, namely Cp and Cv. All solids and liquids do have only one specific heat, whereas all the gases do have two specific heats, namely specific heat at constant volume, denoted as Cv, which can be defined like this. Cv is defined as the amount of heat required to increase the temperature of unit mass of gas through 1 degree centigrade at constant volume. Pictorially, if the gas is taken, 1 kg gas is taken in a rigid vessel or rigid container, and if the increase in temperature is to be 1 degree centigrade, the amount of heat supplied to the gas is known as Cv, whose units are kilojoules per kg degree centigrade or kilojoule per kg Kelvin. As I had already mentioned previously, 1 degree centigrade rise in temperature is equal to 1 degree Kelvin rise in temperature. The gas is taken in the rigid vessel because the volume of the gas should be kept constant for defining Cv. Coming to next, specific heat at constant pressure. Its definition can be given as Cp is defined as the amount of heat required to increase the temperature of unit mass of gas through 1 degree centigrade at constant pressure. Pictorially, the gas must have to be taken in a piston cylinder arrangement, because whenever heat is supplied to the gas, the pressure would like to increase. To keep the pressure of the gas constant, the gas must have to be allowed to expand. Hence, it should be taken in a piston cylinder arrangement. Here, the gas does work on the surroundings while expanding to keep the pressure constant as the heat is supplied to gas. The mass of gas taken is 1 kg in the piston cylinder arrangement. The rise in temperature should be 1 degree centigrade. Then heat supplied at constant pressure is taken as Cp, kilojoule per kg degree centigrade, or kilojoule per kg Kelvin. For any gas, specific heat at constant pressure is always greater than specific heat at constant volume. Cp is always greater than Cv, because in the case of constant volume heating, all heat supplied is solely being used for increasing temperature of gas alone. But in constant pressure heating, the heat supplied to gas is simultaneously being used for increasing temperature of gas and also for doing external work. Hence, for the same gas and for the same rise in temperature, it is required to give more heat in the case of constant pressure than in constant volume. The difference between specific heats of a gas is nothing but characteristic gas constant of the gas. For example, for air, Cp is equal to 1.005 kilojoules per kg degree centigrade. Cv is equal to 0.718 kilojoule per kg degree centigrade. R is difference between them, which we have already calculated earlier, that is 0.287 kilojoule per kg degree centigrade. The ratio between the specific heats of a gas is known as gamma, also called as Adiabatic Index of Gas. The reason why it is called Adiabatic Index is this gamma would be seen in the equation of the adiabatic process in future, which is PV to the power of gamma is equal to constant, which is the adiabatic equation of ideal gas. Combining these two relations, Cp can be written as gamma by gamma minus 1 into R. Cv is R by gamma minus 1.